Let me go ahead and start recording. Okay, so today we're going to talk about basically just in general molecules, just sort of set up that idea. But more importantly, and this is what goes with today's lab, we're going to talk about naming compounds. So we call this nomenclature. So you'll see this word from time to time. So nomenclature is just the way in which we name compounds. Okay, so first of all, let's talk about, if I can get my slides to go here. There we go. Okay, so just set up the idea of what is a compound. Okay, so a compound is just a substance composed of two or more elements combined in a specific ratio, and this will become important later, specific ratio, and held together by chemical bonds. Try to get rid of that little bar down at the bottom. There we go. Okay, so basically a compound is just a couple atoms put together, maybe a few atoms put together, be even huge, would be a lot of atoms put together. Okay, but the point is that they're put together in a specific ratio, okay, and they're held together by chemical bonds. So an example of this would be water. Okay, so what do we mean by specific ratio? Well, by that we mean water is specifically H2O. It's one oxygen and two hydrogens. If we have something else, if we have something like H2O2, okay, now that's peroxide. Okay, that's a completely different compound. Okay, so it's important that we have this specific ratio to make up that specific molecule or that specific compound. They also give us the example of salt. Okay, so sodium chloride, this is just normal table salt. Okay, if it's put together any other way, so if we have, for instance, calcium chloride, or if we have, this is not possible, but if we have something like this, those are completely different compounds. Okay. With these two specific examples, this is good because this would be an ionic compound. We're going to talk about naming those in just a second. And the other would be a molecular compound. Okay, and we're going to talk today about how to name these, and we name them a little bit differently. Okay, so ionic compounds is where we'll start. It's not that complicated, but it's a little more complicated than naming molecular compounds. And then we'll talk a little bit more about molecular compounds, and we'll talk about their naming at the end. Okay, and this will go perfectly hand in hand with your lab today. Okay, so today's lab has everything to do with naming compounds. Okay, so we're going to start out by talking about naming ions and ionic compounds. So I showed you the example before of an ionic compound. So I showed you sodium chloride. Okay, we call it an ionic compound simply because it's made of ions. Okay, so ions make up ionic compounds. Okay, so ions can be anything from, here we have an example of a potassium ion, so K+. So they can have a positive charge, or they can have a negative charge, like chloride ion. Okay, so Cl-. Okay, so those are examples of ions. If we are a positive ion, we call this a cation. So CAT, just like cat, the animal. Cation. And this is an anion. Just so we're familiar with those terms. Okay, so if it's positive, we call it a cation. If it's negative, we call it an anion. So if we want to name things like cations, so if we have a monoatomic, so mono just meaning one, atomic meaning it's an atom. Okay, we name this by just adding the word ion to the name of the element. Okay, so for instance, here we have a potassium ion. So we name this just as I said. So it's the potassium, and since it's ionic, refer to it as potassium ion. In this particular case, potassium can only have one charge. It can only be a +1 ion. So there's no need to give any other information. Okay, so potassium ion, that's all we need to say. Okay, we'll talk more about why I say there's no other charge there in just a second. Okay. Next one here, we have a monatomic anion. So again, mono just one, and an anion meaning it's negative. Okay, well these we actually have to change the name of. Okay, so it's more than just adding the word ion. So if we have an anion, we take the base name, so for instance, here we have chloride ion. Well, base name would be chlorine. Okay, so just straight from the periodic table, chlorine. And how we name it, that it's an anion, is we change the ending to IDE. So here we have, so normally it would be chlorine. Okay, that's our normal name for Cl. Okay, and so we change the ending. So we drop off this I and E, and we change it to IDE. Okay, and that indicates that it's an anion. And sometimes you take off more than other times. Okay, so here we have oxide ion, which is of course from oxygen. So oxygen, so oxy, we'll change OXY to OXIDE. So OXYGEN, we change to OXIDE. Okay, so you just take off the ending and change it to IDE. Now, there's some ions that can form more than those that can have more than one charge, and this typically happens with your cations, so your positive ions. And this is typically going to be your transition metals. Okay, so all those things down in that little middle step. Okay, well these can have more than one charge, so we have to indicate it a little bit different way. Okay, so we can say things like ferrous and ferric. Okay, and these indicate the charge. So OUS means it's the smaller charge, and IC is going to mean it has the bigger charge. So it doesn't necessarily correspond to +2 and +3. OUS just corresponds to the lower charge, and IC refers to the bigger charge. This is a little more outdated nowadays, and some of them you can't do this with. So more traditionally now, the way it's named is by adding a Roman numeral. So we would just say, so for instance, we would say iron 2. Okay, and then written with symbols, you write it with the symbol, the chemical name or the chemical abbreviation, the chemical symbol, with a Roman numeral in parentheses. And so you see down here manganese 2 ion. Okay, so more traditionally we would say this is the ferrous ion. Okay, and we would know that that was iron +2. Or we would say ferric ion. We know this is iron +3. But more modernly we would say iron 2 or iron 3. Okay, it's just a little bit easier. Okay, so here's some examples of ions for you. Okay, so some ions have only one charge. Okay, so things like aluminum. Aluminum's always going to be +3. And you have things like barium, calcium. Okay, so typically these are only going to have one possible ion, things like potassium, silver. And you may be wondering, how do I know that? And I'm going to show you how I know that. Okay, so I'm going to share a periodic table with you. And just quickly, let's talk about how do I know that it's only going to have one charge. Okay, so here's our periodic table. Okay, so the way I know that certain ions are only going to have one charge is based on where they are in the periodic table. Okay, so if I had alkali metal, alkali earth metal, okay, these are only going to have one possible charge. So if it's in my first column here, these are always going to be +1. Try to make this a little bit neater. It's hard when my screen's up like this. +1. Okay, and if it's in the second column, these are always going to be +2. You're not going to see any other ion. So you're never going to see sodium, for instance, as anything but a +1 ion. You're never going to see magnesium as anything but a +2 ion. Okay, and if we come over here to the right-hand side of the periodic table, okay, typically you're only going to see oxygen specifically as -2. On the very rare occasion you have a peroxide, you might see it as something else. Okay. Then over here our halogens will always be -1. Okay, so those are pretty much absolutes. Okay, then the things below oxygen here, sulfur, selenium, those can be invariant, but typically oxygen will always be -2. Your halogens are always going to be -1. And then moving over, aluminum will always be +3. Okay, so that's just sort of some base level knowledge that we have. So when it comes to getting into this middle section, okay, so our transition metals, okay, this is where you're going to start to have multiple charges. So something like iron we just saw can be iron 1, 2, or 3. Okay, so we don't know so much what charge iron is going to have. Okay, and the way we know it, we'll look at in a second, based on how we name it, and based on how we write the formula. Okay, but right away we don't know. However, something like silver will almost always be +1. Okay, that's not strictly true, but for our purposes, it's just fine to say that silver will always be +1. Okay, so there's some things that we know. Okay, and this is how we base on everything else on. So when you come to writing oxidation states and all this other stuff later on, this is the same way you'll do it. You have to find things that you know and expand from there. Okay, so that's just the base level knowledge, and now let me show you how you use it. And you can find these charges anywhere. This is not special knowledge that I have. You can find this other places as well. Your book should have this as well. Okay. Okay, so coming back to our slides now. So here you can see they have a few ions here listed out. So again, things like copper can be copper 1, copper 2. And again, that's because it's your transition metals. Whereas you see things like silver here, +1, even though it's a transition metal, still only has one well-known charge. But things like sodium, your group 1, potassium, group 1. Okay, certain things are only going to have one charge. And that's pretty much how we're going to base the next little bit of this talk on. And again, barium 2 is group 2, so that would be a +2. Aluminum, I told you, would always be +3. Okay, so here are some typical charges you might find. Okay, then anions. These are all your halogens. Okay, so bromine, chloride, fluoride. So your halogens, and then hydride. So hydrogen can be +1 or -1. Usually it's going to be +1. Okay, then you have things like nitride. Okay, so nitrogen can be -3, oxide -2, sulfide -2. Okay, so you can kind of use these to help you with what's to come today. So in terms of naming, in terms of what we're going to talk about with the slides. Okay, so how are we going to get the names of ionic compounds? One good place to start is first knowing how to write ionic formulas. Okay, so here we have aluminum oxide. Okay, and you see the formula here is Al2O3. Okay, so how do we come up with that? So why isn't it just, I don't know, why isn't it just AlO? Why is it not aluminum oxide? So in order to understand where this comes from, you have to know what I just told you. Okay, so you have to understand the charge first. So the first thing you have to know, okay, so if we weren't sure what aluminum was, well, that's something kind of have to know. Okay, and since aluminum only has a +3, it's easy. It's kind of easy in this case. Okay, so we need to know two things for this. First, we need to know oxygen is almost always going to be -2. Okay, so we can go ahead and write oxygen 2-. Okay, and then we need to know aluminum is going to be +3. Okay, there are situations where you won't know one of the charges, and we'll get to that as well. Okay, but this is a case where we know both charges. If it's a case where you know both charges, they call this the crisscross method. So you can take this charge, cross it over, take this charge, and cross it over. Okay, so you end up with Al2O3. So 2 aluminums and 3 oxygens. And the reason you do this, we want the charges ultimately to end up to be equal to 0. Okay, there's no charge that's indicated here, so it's not saying, make a -2 charge compound. No, It's just a neutral compound, so it has to have a charge of 0. Okay, so if we say aluminum has a +3 charge, and we say 2 times +3, okay, this is of course +6. And if we say oxygen is 2 minus, okay, then we say that we have 3 oxygens. Okay, so remember the subscript means that there's 3 of them. Okay, so this is of course -6. So +6 and -6 give us 0. Okay, so you always have to make your compounds add up to a 0 charge, and that's what we're ultimately after. Okay, so this will help you with naming them, so you can go from a name to a formula, or you can go just from knowing which substances are there to a formula. Okay, but today we're specifically going to focus on naming. That's the whole big picture for today. But it's important to know where these formulas come from in order to understand naming. Okay, so formulas for ionic compounds. Okay, so if a compound contains a metal and a non-metal, the compound is going to be most likely ionic. I can't really think of any examples where it's not. Okay, so and then you have two possibilities. So you have metal cation that can only have one possible charge. These are your alkaline metals and your alkaline earth metals. Okay, so how we're getting these, and we'll go deeper into this, but this is just an overview. Okay, so the way you're going to name these is you're going to name the metal first. Okay, so for instance, we would say aluminum or silver. Then you're going to add IDE to the root name of your non-metal. So if we had something like this, if we had something like AgCl, for instance. Okay, so we name this as the metal first, silver. Okay, then the root name of the non-metal, which is chlorine, change the ending to IDE. So this would be silver chloride. Oh, sorry, let me try to get rid of that. There we go. Okay, then we have the possibility where our metal cation has more than one possible charge. So these are going to be things like your transition metals. Okay, so you're going to name the metal first, specify the charge with a Roman numeral, and then add IDE. So this would be an example of, I don't know, maybe I have something like copper chloride. Okay, so the problem here is that copper has more than one charge. So I would have to name this as copper, and then I would have to determine the charge of copper. In this case, it's, so I'd say copper 2, and then chloride. Okay, so again, changing the ending to IDE. And this one, just to write out, would be silver. Okay, and there's nothing special about chlorine, it's just the one I picked. Okay, so those are the two different naming styles. And we'll get into that a little bit deeper now. Okay, so naming ions and ionic compounds. Okay, so if we're going to name an ionic compound, first thing we do is we name the cation. And notice we didn't say potassium ion chloride or something like that. So you omit the word ion. Okay, so you can just forget about the word ion. And then, if it has more than one charge possible, if the cation has more than one charge possible, we're going to use a Roman numeral to indicate the charge of the cation. Okay, then we're going to name the anion, of course, omit the word ion. Okay, and then change the ending to E. So change the base name ending to IDE. Okay, if you're naming the anion, you've basically already done that. Okay, so some examples here. Okay, so we have sodium and we have bromine. Okay, so the first thing we're going to do, name the cation, which is the metal. So in this case is sodium. Okay, then our anion would be bromine. Change the ending to IDE, so we have bromide. So if we put those together, we have sodium bromide. Okay, in this case, we don't have to indicate, so in other words, we don't have to say like sodium 1 bromide, because we know sodium only has one possible charge. If there was a possibility for sodium 2, which there's not, okay, I would have to say sodium 1 or sodium 2. Okay, so like the example down here below. So here we have iron and we have chlorine. So if I just said, so instead of saying either of these, if I just said iron chloride, okay, if I just said iron chloride, you don't know whether I'm talking about iron 1 chloride, iron 2 chloride, iron 3 chloride. You have absolutely no idea. So the problem with naming it this way is that iron could have more than one charge. Okay, so if the cation can have more than one charge, you have to give it the Roman numeral. Okay, so we have to use this system. So we can't use this. That doesn't work. Okay, so we have to say, for instance, iron. Then we have to figure out the charge on iron. In this case, it's 2, because remember each chlorine. So how do I know that? You might be wondering. Okay, so here we have iron Cl2. Okay, I know that each chlorine is a -1. I know that I have 2 of them. So 2 times -1 and -2. So that means iron has to balance out a -2. Okay, so that means iron has to be +2 in order to balance out the -2. Okay, so that's how I know the charge on that. Okay, so here I have iron 2 chloride. So here I indicate the charge of iron with a Roman numeral. Because it could also be iron 3 chloride. So here I have -1 chloride times 3 gives me -3. That means iron has to balance out a -3 by being +3. Okay. So I have to indicate, no, it's iron 3 chloride. Okay, so that's where the Roman numerals come in, and that's sort of the naming system. And that's really as complicated as it gets. We'll get into some little more complicated ones with atomic anions right at the end, but really it's no more difficult. You just have to know the charge of the polyatomic. In some ways it actually makes it a little bit easier. Okay, but that's really as complicated as it gets. Okay, so let's name some of these. Okay, so I'll walk you through how some of these are named. So the first one we have, in fact, let's just grab these. And instead of just walking you through what's there, I will do this instead. That's not what I want. Okay, wait just 1 second here. That particular program has an X button. It doesn't always do what you want to. Okay, so a blank piece of paper. That's all I really wanted. Okay, so let's work out this problem like this. Okay, so just 3 compounds to name. Let me just double check you're seeing that the way I want you to. Yeah, okay, so they want us to name these 3 compounds. So let's start with A. Okay, so A. So we have CaO. Okay, so the first thing we have to do with this, we have to decide, okay, calcium. Can calcium have more than one charge? And if you go to your periodic table, you'll see calcium is in the group 2. So the only possible charge for calcium is to be +2. So that's it. Okay, so what that tells me is I can name this without a Roman numeral. So all I have to do is just write the base name of my cation. So calcium. Okay, and then my anion here is oxygen. Okay, but I don't name oxygen as when it's an anion. I don't name it as oxygen. I have to name it as oxide. Okay, so that would be my answer for A, just calcium oxide. Okay, B, I have Mg3 and 2. Okay, so I actually don't need to know what the charges on these two are. The only thing I need to know is that magnesium can only be +2. Okay, so since it can only have one charge, I just write magnesium. Okay, and then I just have to name my anion. So here I have nitrogen. Okay, but since it's an anion, I don't name it as just nitrogen. So I get rid of my ending. So like I said, sometimes you get rid of more ending than in others. I change the ending to IDE. Okay, so this becomes magnesium nitride. Okay, so those are two examples where you only have one version of your cation possible. Okay, this last one, we have iron. We have 2 of those. We have sulfur. We have 3 of those. Okay, so this is one we have to decide, okay, is there more than one possible cation? Is there more than one possible anion? Okay, so how do we do that? Okay, so the first thing we have to do is we have to know, okay, iron is a transition metal, so that means it can have more than one anion. So I'll just put a question mark there. I don't know what the charge of is this going to be. Okay, then I have to decide, okay, sulfur. What ion can sulfur have? Okay, well, it's under oxygen, so I know sulfur can probably be -2. Okay, so I have 3 sulfurs, so I'll say times 3, which gives me 6. Okay, so I have a -6. Now iron has to balance out -6 completely. So we have to have the charge equal to 0. Okay, and you'll notice I have 2 iron in this compound, so I have to divide by 2. So this gives me, of course, -. So that tells me that each iron has to balance out -3. Okay, so that means each iron has to be +3. And then, of course, +3 times 2 will give me +6, which cancels this. Okay, so +6 and +6 cancel. So I know then, now that iron has to be +3. Okay, even though I have 2 of them, it's still +3 on its own. Okay, so the way I would name this, let's get rid of this. Okay, so the way I would name this, first I name iron. Okay, then I said it's +3. So draw parentheses, and then your Roman numerals, and you can connect them with the bar or not. Either way is fine. Okay, so I have iron 3, and then my anion is sulfur, but it's of course an anion, so I would write sulfide. Okay, so the name of this compound would be iron 3 sulfide. And you can check your answers here. So calcium oxide, magnesium nitride, and then iron 3 sulfide. So just what we said. And so you kind of have to know a little bit about charge when it comes to ions that can have more than one charge. Okay, so now we're going to go the other way. Okay, so now here we were going from formula to name. Here we're going to go from name to formula, which I think sometimes this is a little bit easier than going the other way for students. Okay, so let's work these out the same way. Okay, so I'll just grab these. And we'll go back to the paper. Okay, so here's our question. Okay, so they've asked us to name A, B, and C here. Make that a little bit bigger for you. Okay, so let's start with A. Okay, so they're giving us mercury, and they've told us this is mercury 2 chloride. Okay, so now that we have the name, we're given a charge here, so mercury, chemical symbol Hg. Okay, so we can just write this as 2 plus. Okay, then we have chloride, which we know is Cl minus. Okay, so we have the chemical symbol for each. We know their charge. Okay, so now we can do the little crisscross method. Okay, so now we can take this, move it here, take this -1, put it here. So we end up with HgCl2. Okay, so this would be mercury 2 chloride because we need 2 -1s to balance out the +2 of mercury. Okay, B, give us lead 2 bromide. Okay, we're going to do a similar thing here. So lead, I'm going to write it over here to the side. Lead we have, they're telling us is 2 plus. Bromide, we know is 1 minus. Okay, so a similar thing here. So this charge will come here, and this charge will come here. Okay, there are instances where this doesn't quite work so easily. Okay, but for purposes of our conversation, this will work just fine. So this was the answer to the first one. So it's very rare that this won't work, but there are times when it won't work. Okay, so the answer for this one will just be PbBr2. Okay, so that would be your final answer. Last one. So C, they give us potassium nitride. Okay, so this time they don't tell us anything about the charges, right? So we have to know that potassium can only be 1 plus. Okay, and then we also have to know that nitrogen is going to be -3. And this has to come from our knowledge. That's not a good looking in. Okay, so if I want to write the formula for this, now I know that I have to have 3 plus charges to balance out this -3. So you can do your crisscross method, which will end up with K3N. Okay, that would be your final answer. Okay, so those are your A, B, and C for this one. Okay, and you also have those answers here in the slides. Okay, so that's how you're going to name ionic compounds. Okay, so the opposite, or not the opposite, but the other side of this, we're going to talk about covalent compounds. So this would be your non-ionic compounds, just your basic chemical formulas, things like water, methane, ethane, ethylene, these kind of things, ethanol, okay, your alcohols. These are all just covalently bonded compounds. So these are just your basic covalent molecules. Okay, so when compounds form between elements with similar properties, electrons are not transferred from one element to another, but instead shared. Okay, so with ionic compounds, each ion retains their own electrons, or even you can think of it as like sodium donating an electron to chlorine to give it chloride and sodium ion. Okay, but in covalent bonds, we're not transferring any electrons. What we're actually doing is we're sharing electrons. Okay, and this approach is known as Lewis theory of bonding, named after Lewis. Okay, you'll get into drawing Lewis structures more like in Chem 2. Okay, but this is the basic idea. So you write the chemical symbol along with their electrons, okay, then you put them together. Okay, so more traditionally we would write this like this. So H bonded to an H, where the line in the middle represents 2 electrons. Okay. So you don't really need that right now, but that's basically, if you see stuff like this, this is what you're looking at. Okay, so this is known as covalent bonding. Okay, and this sharing of electrons is called a covalent bond. Okay, so the reason you need to know this information is because it sets them aside from ionic compounds. So these are covalent compounds rather than being ionic salts. Okay, or ionic compounds. Okay, so that's what we're going to talk about now. Okay, so a molecule, similar to a compound, basically the same thing, is a combination of at least 2 atoms in a specific arrangement held together by chemical forces, what we call chemical bonds. Okay, and a molecule can be either an element, meaning it's just one type of atom, or it can be a compound, meaning it's more than one type of atom. Okay, we talked about this a little bit at the beginning. Okay, but different samples of a given compound always contain the same elements in the same ratio. This is called the law of definite proportions. Okay, which sounds more complicated than this. This again just means that if I have any given compound, if I make it out of elements, it has to have that specific ratio. Okay, so something like CO2, carbon dioxide. Okay, this is what we exhale, right? So if we have anything other than CO2, then we have a different molecule. So for instance, we have CO. Okay, now this is carbon monoxide. This is a toxic gas. Okay, so it has completely different properties because it's a completely different molecule. Okay, so just by simply having a different formula means it's a different molecule. Okay, so that's all that means. So any molecule has a specific formula, and it comes together in a specific ratio. That's what the law of definite proportion means. Okay, and if I have a different ratio, okay, then I have a different compound. That's all it's trying to say. Okay, and this is a very similar idea. So law of in multiple proportions. So again, this tells us that if I have different ratios, then I have different combinations, or different molecule, I mean. Okay, so if 2 elements can form 2 or more different compounds, the law of multiple proportions tells us that the ratio of the masses of one element that combine with a fixed mass of the other element can be expressed as in small whole numbers. Okay, again, it just means that if we have atoms coming together in different ratios, then we have different compounds. Okay, so coming back to this real quick, law of definite proportions also means that this is always going to be 1 to 2. This will always be 1 to 1. And you can do the math based on the mass. So oxygen here compared to the mass of carbon gives you this ratio. And you notice it's not exactly 1 to 1 or 2 to 1. Okay, this is based on the mass, whereas this would be based on the atoms. Okay, but that's more than you really need to know for today. Okay. And again, if you have more than one combination of the atoms, so if you have CO versus CO2, those are different molecules. That's really all it's trying to say. Okay, so here we have carbon dioxide versus carbon monoxide. Okay, so the mass ratio of oxygen to carbon in carbon dioxide is 2.66 to 1, and the ratio of oxygen to carbon in carbon monoxide is 1.33 to 1. Okay, the ratio of 2 such mass ratios can be expressed as small whole numbers. Okay, meaning that we write this out as something like CO2 and CO. Okay, we don't really write out CO 2.66. Okay, that doesn't work. Okay, but it's easier just to write, okay, I have 2 oxygen atoms and 1 carbon atom. That's a lot easier. But if we do the mass ratio, so this This is having to do with the mass. Okay, so if instead of just saying I have one carbon atom and two oxygen atoms, if I instead look at their mass, I would come up with a ratio like this. But it's easier to think in terms of this. So this is all this is trying to say. And this is again for covalent compounds. Okay, so we have two types of covalent compounds. We have diatomic molecules. These can be either heteronuclear or homonuclear. Okay, then I can also have atoms containing multiple atoms, so polyatomic molecules, or molecules containing multiple atoms, what I'm trying to say, polyatomic molecules. Okay, so homonuclear and heteronuclear. Homonuclear, this would be something like hydrogen, so HH. Okay, where heteronuclear would be something like CO. Okay, so carbon and oxygen, hydrogen, hydrogen. So homo just meaning the same, hetero meaning different. Okay, then lastly, I have polyatomic molecules. This would be like CH4. Okay. So I can have many atoms in a molecule, or I can just have two. Okay, and if I just have two, it has special names. So homodiatomic, heterodiatomic. And everything other than that would be polyatomic. And those names really aren't used all that often, to be honest with you. Just so that you understand that molecules can come together in ways. Okay, so now let's talk about formulas. This will come in handy when we start to get into naming. Okay, so a chemical formula denotes the composition of the substance. So something like H2O. Okay, a molecular formula shows the exact number of atoms of each element in the molecule. Okay, so chemical formula tells us what's there. Molecular formula tells us exactly how many of each atom and each element is in the molecule. So H2O, HOH, HOH, these are all examples of molecular formulas. Okay, and then we can also have this ball and stick type. So we have a couple different ones here. Okay, so we can write it out with chemical symbols. These would be more like Lewis structures. This would be like just a chemical formula. This is called a ball and stick, where we have hydrogens represented as the white balls, and then oxygens, which you're not gonna be able to see my red very well, are you? Represented as the red balls. And then these sticks in the middle, so these are the balls and these are the sticks. The sticks represent the chemical bonds. Just like with our Lewis structure, these sticks represented our chemical bonds. Okay, and then we have what's called the space filling model, which this shows sort of how big the electron cloud is, how much mass they would take up, how much room they would take up. Okay, but they all mean exactly the same thing. That's the point I'm trying to make here. They all mean the same thing. Okay, these bottom two would be examples, well, kind of the bottom four here would all be examples of structural. Okay, so they're all examples of chemical and molecular formulas, but the ones that actually show you the structure are called structure formulas. Why? Because they show you the structure of the compound. So they just give you a little bit more information, but they all kind of give you the same, the same basic idea. But the structure formula gives you more information because maybe you have a complex molecule that you're not familiar with, and there's some I could show you, but it's not necessary for this conversation. Okay? Okay, so what we're really interested in today is naming these. Okay, so naming molecular compounds. Okay, so here they talk about binary molecular compounds, which are substances that contain just two different elements. Okay, so how are we going to name molecular compounds? Okay, so the first thing we do is we're going to name the first element that appears in the formula. Okay, then we're going to name the second element that appears in the formula, changing the ending to IDE. So this is similar to ionic compound. Okay, but this is only done in a very specific circumstance. So this is only done with binary molecular compounds, meaning we just have two atoms. So outside of binary compounds, molecular compounds, we're going to name them a different way. Okay, but here we have hydrogen chloride. Okay, so we have HCl. Okay, so hydrogen is the name of our cation, so the first element. Then chlorine, change the ending to IDE. Okay, then we have HI, hydrogen iodide. Okay, this is also known as hydrochloric acid, more specifically. Okay. But for now, that's not what we're talking about. Okay, that would be if we're talking about naming acids. Okay, so if we're just going to name it according to this nomenclature, we would name it hydrogen, chlorine, change the ending to IDE. Same with the other one. Okay, but what's different about naming molecular compounds is we use a different numbering system. Okay, so here we're going to use Greek prefixes. Okay, so this is how we denote the number of atoms in each element. Okay, so let's use an example we know pretty well. So CO2. Okay, so this is my chemical formula. This tells me I have 1 carbon and 2 oxygens. Okay, but what if I wanted to express this with words? So how do I tell people that I have 1 carbon and 1 oxygen? Well, we're familiar with this, right? Carbon dioxide. Okay, so where do those names come from, though? Okay, so this is our Greek numbering system. So mono is 1, di is 2, tri is 3, and you can kind of see the rest. Okay, all the way up to octa, deca. Okay, so some of these we're kind of familiar with, like December, November, October. Okay, so we're kind of familiar with these. Mono, we're pretty familiar with di and tri. They kind of sound like what they are. Okay, if the other ones you may have to kind of learn. So like tetra is 4, penta is 5. Okay. A lot of these you may remember from things like geometry, like hexagon, heptagon. Okay, so it's all the same system. So if you learned it before, you know it now. But back to my example here. So how do I know that this is carbon dioxide? Okay, so I have 1 carbon, so that would be mono. So I could write this. I could write mono carbon. Then I have 2 oxygens, so I would say dioxide. Okay, so why isn't this named monocarbon dioxide? And the reason that is that if the first word is just 1, we leave off the word mono. Okay, but if it's in the second word, like this, we have to include it. Okay, so this would be carbon dioxide. Okay, if we instead had this, we had carbon monoxide, we would have to include it still. Okay, but I wouldn't say monocarbon monoxide. Okay, but I would have to say carbon monoxide. So you always include mono if it's in the second word. Okay, but back to my example of carbon dioxide. So 2, I have to say di. If this was instead of 3, I would just say tri. Okay, so that's where those names come from. Okay, so we're going to use these Greek prefixes to name molecular compounds. And again, just get to know these. Okay, so some examples here. Okay, so carbon monoxide tells me I have 1 carbon, 1 oxygen. Again, same example I use, carbon dioxide. Here, di tells me I have 2 oxygen. Sulfur dioxide, again, tells me I have 2 oxygen. Tri tells me I have 3. Nitrogen dioxide, so I have 1 nitrogen, 2 oxides. But notice here, okay, see, here's another example. Here I have N2O5. Okay, so now I have more than 1 nitrogen. So first of all, I would say nitrogen, and the second word oxide, of course. But now I have to say how many. Okay, so I have 2 nitrogens, so I'll say dinitrogen. I have 5 oxides, so I'll say pentoxide. And notice we drop the A there. Usually when there's 2 vowels close together, unless it's an I and an O, like if it's 2 O's close together, you don't say like monoxide, you just drop one of the O's. But if it's an I and an O, then you keep them. Okay, and if it's an A, you drop it as well. Okay, this is just kind of based on more like tradition, kind of, you could think of it that way. Okay, but if you have like an I and an O, keep it, otherwise you pretty much drop it. Okay, and again, mono is omitted from the first element. Okay, and they give you a note here. Drop the O and the A when it comes to oxide. Okay, so that's how you're going to name molecular compounds. And that's really as complicated as it gets. You're just indicating how many of each atom you have by using the right prefix. Okay, so some examples here. So we have in F3, okay, so we just have one nitrogen. So we're not going to say mononitrogen, we're just going to say nitrogen. Then we have 3 fluorides, so we'll just say tri, and then the name of the element, or the name of the ion, fluoride. Okay, so 3 fluorides. The next one here we have N2O4. Okay, so we have 2 nitrogen, so we'll say dinitrogen. That's important because we have more than one. If we just had one, we would leave it off. Okay, then we have 4 oxides. So we have to go back to our Greek prefixes and find the one that goes with 4, which is tetra. Okay, we're going to drop the A, so this becomes tetroxide. Okay, so that's really all there is to it. So any bimolecular compound, this is how you're going to name it. And when we start to get bigger than this, they start to get a little more complicated. Okay, but if it's a binary molecular compound, this is all you need to know. So just know your Greek prefixes, know how to use them. Okay, so now here we're going backwards. So here we have sulfur tetrafluoride. Okay, so I don't see the word mono in front of sulfur, so I know I just have one. Now I see tetra. Okay, so now I have 4 of whatever this is, fluoride, so I have 4 fluorides, so SF4 is enough. Okay, then I have tetraphosphorus decasulfide. So this tells me I have 4 phosphorus atoms. Decasulfide tells me I have 10 sulfides, so P4S10. Okay, so that's really all there is to naming molecular compounds, as long as they're binary molecular compounds. Again, when they start to get bigger, they get a little more complicated than that. Okay, so very last thing we're going to touch on today. And this again, all of this goes hand in hand with the lab for today. Okay, so this is good. Okay, so the last thing here is polyatomic ions. Okay, so what are you going to do if you have a polyatomic ion? And what is a polyatomic ion? Okay, so a polyatomic ion is just what it sounds. So poly meaning more than one, atomic meaning more than one atom. Okay, ions. So it's just what it sounds like. It's an atom with an ion with more than one atom involved. Okay, so here a polyatomic ion would be something like phosphate. Okay, so PO4, and then notice it's charged 3 minus. Okay, so that tells you that the whole thing, this whole PO4, has a charge of 3 minus. Okay, so that's what a polyatomic ion is. Okay, so and these can be involved in ionic bonding, just like if instead we had, I don't know, an ion with a 3 minus charge. So suppose this was sulfur 3 minus, okay, instead of PO4. You're going to treat it just exactly the same. Okay, if it was oxygen or something. You're just going to treat this whole thing as having a 3 minus charge. So you're going to write your formulas exactly the same way. Okay, so you can do your crisscross method. Okay, this time you're using this charge. Okay, so bring that over, then use this charge and bring that over, just like you did before. So that's how we come up with the formula. And again, remember, the entire compound has to be equal to 0. Okay, what we're really after today is the naming. Okay, but let's look at some polyatomic ions first, and let's look at their names. Okay, so these can be anything from something like ammonium, so the ion of ammonia is ammonium. Hydronium, which is H3O+. These are ones you're probably not going to see today. You may see ammonium, but probably not the other two. So remember ammonium. Okay, that's a good one to know. Okay, then there's some others down here. So these have names like acetate. So C2H8O2-. So if you've heard of acetic acid, the reason that's acetic acid is because it comes from acetate. Okay, then you have things like carbonate, chlorate, chlorite. Notice these two names here are very similar, chlorate and chlorite. What's different about them? The number of oxygens. Okay, so chlorite refers to the one with less oxygens, 8 refers to the one with more oxygens. Okay, and then you have things like chromate, cyanide, dichromate. There's really no special trick or anything I can teach you for these. These are just things you kind of have to memorize or have a table handy. So today you'll be able to have a table handy. I don't know about for your exams, but typically these are things you're going to need to memorize. Okay, and then you have things like sulfate, bisulfate, all these different things. Okay, so there's lots of these. Okay, so here's some more important ones. Sulfate you'll see a lot. So sulfate and sulfite, get those two confused. Then you have hydroxide, OH minus, nitrate, nitrite. Okay, so you can use lists like these to help you with the names. Okay, but just understand that this whole thing, NO3 minus, that whole thing is nitrate. Okay, so if you see nitrate, just know that it's paired together, it has an overall -1 charge. Okay, so how are we going to name these? So you're going to name them. These are going to be ionic compounds. So just like what we talked about at the very beginning, the only difference now we have polyatomic ions. Okay, so if we have Fe2SO4 3. Okay, so the first thing we have to know, okay, well, we know iron can have more than one charge. So how are we going to figure out what that charge is? So first we have to go back to sulfate. What's my charge on sulfate? Okay, well, I know sulfate has a -2 charge. Okay, so I have -2. I know I have 3 of them. Okay, so this is going to be equal to -6. Okay, so that means that both of these ions have to balance out -6. So divide by 2 gives me -3. So now I know iron has to balance out a -3. Each iron has to balance out a -3. So that must mean iron is +3. So if I'm going to name this, now I know the charge of iron. So if I'm going to name this, I'm going to name it iron, indicate the charge with 3, okay, and then sulfate. So just the exact name of the polyatomic ion. Notice I didn't change anything. Okay, so if we go back here, sulfate, that's the exact same name. So that's all you have to do. Just write the name of the polyatomic. So indicate the charge of the cation, and then just write the name of the anion. Okay, so what if we have an ion that doesn't have more than one charge? So here we have AlO3, OH3. Okay, so I'll get rid of this so I have some room to write. Okay, so AlOH3. Well, I know aluminum has to be +3. I know hydroxide has to be -1. Okay, so I have 2 ions that only have 1 charge. So I really don't have to indicate anything here. So since aluminum can only be +3, I just write the word aluminum. Okay, so no need to write Roman numerals. Okay, and what kind of salt is this? Well, it's the hydroxide salt. So I just write the word hydroxide. I don't have to change anything. And going back in OH minus, just the name hydroxide. I don't change anything. Just write the word hydroxide. And the last one is mercury oxide. I think you can do that one. Now that you've seen a couple, I think you can do it on your own. Okay. Okay, so that's everything you'll need to know, hopefully, about okay, so if I have binary acids, and you may be wondering, okay, what is a binary acid? So just like with a binary molecular compound, it just has 2 things in it. So something like HCl. Okay, so this is a binary acid. So the first thing you're going to do when you encounter a binary acid, you're going to want to write hydro. Okay? So all binary acids start with the name hydro. Okay? That indicates that I'm talking about a binary acid. The next thing to do is I'm going to name my anion. So chloride. Okay? But I'm not going to keep this as chloride. So I know it's chloride, but I'm not going to keep it as that. What I'm actually going to change it to, so now I'm going to change my ending of chloride to chloric. So this becomes hydrochloric, and then I write the word acid. Okay, so that's hydrochloric acid. See if there's any others. Okay, and that's the only structure that these have. Okay, so first write the word hydro, then write the name of your anion, change the ending to ic, then write the word acid. That's all you need to know for naming binary acids. Every one of them works exactly the same way. Okay, so hydro, name of the anion, change the ending to ic, then write the word acid. Okay, when it comes to naming oxyacids, this is where it gets a little more complicated. So we have something like H2SO4. Okay, so when you're naming oxyacids, first thing you have to do is identify the polyatomic ion. So here we have SO4, so sulfate. Okay, so where this gets a little bit tricky is the endings. Okay. So if we have, just looking for something real quick here. There we go. So this one is sulfate, right? But we could also have sulfite, so SO3. So this would be sulfite. Okay, and so where this gets tricky is these endings. So if you have 8, it becomes ic. If you have ite, it becomes us. Okay, so a handy way of remembering this is you can say, I caught a bad case of 8 ic, ite, us. Okay, so 8 to ic, ite to us. So what that means is sulfate becomes sulfuric acid. Okay, so this would be the name of the acid. If you have ite, so 8 becomes ic, ite becomes us. So this would be sulfur us acid. And then you write the word acid just to let you know it's an acid. Okay, but that's all there is to it. So you have to know whether it's an 8, ite, and then change the ending to ic or to us. Just remember, if it's 8, change it to ic. If it's ite, you change it to us. Okay, but that's all there is to it. That should be as complicated as it gets.